So we're finally coming to the end of this interminable chapter 10 here, chapter 6 here rather, with 6.10, part B. We'll be looking at the inverse of the hyperbolic functions that we were talking about in the last video. Here are our definitions of those inverses, and hopefully the fact that there are natural logs in the definitions wouldn't be a big surprise, because remember, the hyperbolic functions themselves were all defined in terms of e to the x. Sinh was e to the x minus e to the minus x over 2, and cosh was the same thing with the plus, right? We had these definitions for sinh and cosh, meaning all of these also involve the e's. So that does mean that the natural logs would be the pretty obvious inclusion in the inverses. The domains here are all set up simply so that the logs themselves will work out. We know we can't have a negative inside a log, so we've got restricted domains to avoid that. All right, the first thing says, let's see why at least a couple of these formulas make sense. I'm actually just going to work with one of them. The algebra is a little hairy, so we'll get through one of them and see that, hey, that works, and we'll just kind of make the assumption that the other ones do as well. Let's consider the function y equals hyperbolic sine of x. And just going and grabbing that definition from last time, that is e to the x minus e to the minus x over 2. If I want the inverse function, our standard algebra trick for finding inverses is to switch the x and the y. So I'd write x equals e to the y minus e to the minus y over 2. Now, here's the fun part. I have to solve for y, which is much easier said than done, but we'll get there. Simple, I can just take the 2 and multiply it over here. That's simple enough. And then I'm going to use a little trick. I'm going to say, what if I multiply both sides by e to the y? The reason that I'm doing that is actually so that I won't have any more negative exponents. So this is going to end up looking like 2x e to the y equals e to the 2y minus e to the 0, which is really just 1. Let me bring this term over to the right-hand side to get a 0 here. Like so. And what I actually have here is a quadratic equation in e to the y. Think of this as e to the y squared minus 2x times e to the y minus 1. Something squared minus a coefficient times that thing minus a constant. Something like this is quadratic, meaning I should be able to solve it using a quadratic formula. So that's exactly what I'm going to do. Basically, I'm going to say, let's think of a as 1, b is the negative 2x, and c is the negative 1. And I'm just going to plug all that into the quadratic formula. Now, usually when we solve for a quadratic formula, we say x equals, but in this case, my variable is actually e to the y. So it'll be e to the y equals, and here comes the quadratic formula, minus v would be 2x, plus or minus the square root of b squared minus 4 times a times c over 2 times a. Let's see, let's simplify that just a little bit. That would be 2x plus or minus the square root of 4x squared plus 4 over 2. And if I factored out the 4 under the radical, I'm going to factor out that 4, and I'm going to take it out of the square root as a 2. So what I have left under there is just x squared plus 1 now. And of course, that's going to allow me to divide out the 2's. So I now have e to the y equals x, just 1x, plus or minus the square root of x squared plus 1. Now, e to the y is always positive, right? E to any power is positive. And therefore, I must have a positive value on this side, meaning I'm going to pick the plus on the square root. If I pick the minus, that term would be bigger than that one, and I'd get a negative. So since the left side is positive, the right side must be positive as well. And we'll pick the plus. All right, last but not least, we take our natural log on both sides. And y, which is the inverse function, looks like this. Okay. So the inverse of our original function, which was the hyperbolic sign, is the natural log of x plus the square root of x squared plus 1, which matches what's in the table at the top. You can do a similar type of analysis for any of these, but as you can see, the algebra is a little bit ugly, so we'll just leave it at that one, and we're going to accept the rest of the definitions as stated. So from here on in, if I ever need it, I can use those as definitions of the inverse hyperbolic functions. All right, one physics application of the inverse hyperbolic is a path called Attractrix. If you imagine a person holding a rope that's tied to a boat, shown in this figure, the person starts over here, and the boat starts here. That rope is stretched right along there. And if the person walks up this pier, holding the rope, what's going to happen is the boat's going to follow this path, and that path, that curve, is called Attractrix. Okay? So it's the path the boat follows when the person with the end of this rope, right, here's the rope at the beginning, person's holding the end of the rope, they walk straight up the dock, and the boat follows that path. That's your Attractrix. The equation of the Attractrix will be y is equal to a times the inverse hyperbolic secant of x over a, minus the square root of a squared minus x squared, a being the length of the rope. So let's imagine in our particular problem that our rope is 20 feet long. So when we started, the rope was right here, the boat was exactly 20 feet away from the dock, and we had this nice straight 20-foot rope. That must mean that I could write my Attractrix equation as 20 times the inverse hyperbolic secant of x over 20 minus the square root of 20 squared would be 400 minus x squared. All right, the question then says, find the distance the person can walk. Notice that the person is walking in the y-axis, so essentially this is saying I'm trying to find y. To bring the boat to within 5 feet of the dock. So my person is walking here, y. The distance between the boat and the dock would be here, and that's x. So, to bring the boat within 5 feet of the dock, that means the x value is 5. So all I have to do is plug in 5 for x. All right. So we have 20 times the inverse hyperbolic secant of 1/4 minus the square root of 375. Now, unfortunately, many calculation devices don't have an inverse hyperbolic secant. If you happen to have one that does, more power to you. I know a standard calculator, even a nice TI-84, will not, although some of the more advanced ones might. So I'm going to go ahead and illustrate this problem using these definitions that we had here. So I'm just going to use this definition of the inverse hyperbolic secant, and I'm going to plug 1/4 in for the x's. So I would get 20 times, and the inverse hyperbolic secant is the natural log of 1 plus the square root of 1 minus this value squared, so 1/16, over that value, 1/4. And then we have minus that square root 375. And this now becomes something I can just plug into a calculator. Comes out to about 21.9 feet. All right, so again, physical application of that inverse hyperbolic secant. One example would be Attractrix. All right, let's do a little bit of calculus with these inverse hyperbolics. Here's a list of their derivatives. All of these can be found simply by looking at the original definitions of the inverse hyperbolics, that previous table, and taking the derivatives. We're going to go ahead and kind of prove one of these formulas, but the rest of them we'll just sort of accept as calculated the same idea, same way. So, again, we'll show where 1 comes from. I'm going to go ahead and just, since we did hyperbolic sine last time, let's do hyperbolic cosine. Or inverse hyperbolic cosine. I'm just going to copy the definition of the inverse hyperbolic cosine right from here. And notice, by the way, that the domain goes from 1 to infinity. So for x greater than or equal to 1, this is valid. We can do that derivative. It would be 1 over x plus the square root of x squared minus 1 times, chain rule here, 1 plus 1/2 x squared minus 1 to the negative 1/2 times 2x for the chain rule there. And let's see, I can let these 2's cancel. So this ends up being, in the numerator, I could have this x, or excuse me, 1 plus this x over the square root of x squared minus 1 all over x plus the square root of x squared minus 1. And I'm going to clear the complex fraction by multiplying by the radical x squared minus 1, top and bottom. So on the top, I'll get the square root of x squared minus 1 plus x. And let's see, on the bottom, I'm going to get x times the square root of x squared minus 1 plus x squared minus 1. And I'm going to have to do a little bit of weird algebra here. I had to stop and think about this one for a moment. I'm going to leave the numerator the way it is. And in the denominator, I know it's going to look a little weird, but I'm going to think about this as a unit, and I'm actually going to factor out the square root of x squared plus 1. It's going to leave this x right here, plus, if you divide something by its square root, you get the other square root. I just wrote pluses instead of minuses. Goodness. Let me fix that. That was x squared minus 1. And I'm factoring out the square root of x squared minus 1, leaving us that x, and then dividing that by its own square root leaves the other square root. Now, if I look at the numerator, it's a perfect match for what's inside these brackets, and so I can divide those out. And that's just going to give me 1 over the square root of x squared minus 1. So it cleans up real well. It just took a little bit of algebraic ingenuity to get us there. And again, this was for x greater than or equal to 1. And if you'll notice, hopefully that's what they gave us. If I could find the right piece of paper here. That is exactly what's in the table for the derivative of the inverse hyperbolic cosine. So we are good to go. The rest of them are all done similarly. Lots of crazy algebra involved in these, and we won't go through it all, but we'll just accept now that that list of derivatives is what we're going to work with. So let's practice finding a couple of derivatives for some inverse hyperbolic functions. In example 2. First of all, the inverse hyperbolic cosine of 4x. If I use that formula that we just developed up here, in fact, let me just push that up a little bit, I would have f prime of x equals 1 over the square root. And instead of just x, we have 4x. So I'd have 4x squared minus 1. And then my chain rule times 4 is going to give me 4 over the square root of 16x squared minus 1. This next one, I'm seeing a product here, so let's go ahead and define a product rule. F is just going to be that 2x to the 5th, and g will be the inverse hyperbolic tangent of x squared. F prime then is 10x to the 4th. And for g prime, I'm going to have the rule says 1 over 1 minus x squared, but instead of x, I have x squared. So I'll have 1 over 1 minus x squared squared, and then times 2x for my chain rule. That would be 2x over 1 minus x to the 4th. right, so the derivative of the original function is fg prime. If I multiply those, I would get 4x to the 6th over 1 minus x to the 4th. Plus gf prime, 10x to the 4th, times the inverse hyperbolic tangent of x squared. And that should be it. All right, I'd like to go back to that Attractrix example that we looked at just a little bit ago. And there actually is a typo here. Remember that this was actually 20 times the inverse hyperbolic secant. Make that 20 times there, not 20 plus. Here's the equation of our Attractrix, same as what we were working with before, just instead of 400, I guess I've typed 20 squared here, but that's the same as 400, of course. And our first goal is simply to find the derivative, find y prime. So let's do that. We'd have 20 times the derivative of the inverse hyperbolic secant, which looks like this. Let's see, I have -1 over, this is x, but in my case that would actually be x over 20, times the square root of 1 minus x squared, again mine's really 1 minus x over 20 squared, times, chain rule would give me a times 1/20th here. Minus derivative of the radical, 1/2 times 400 minus x squared to the -1/2, and then chain rule, -2x. Okay, so there's that derivative. I am going to play around with this just a little bit and see if I can clean this up and make it look a lot better than that, because that's kind of a mess. Let's see, those I can get rid of. And I'm going to go ahead and do an invert and multiply on this. I'm going to call that -20 on the top over x square root 1 minus x squared over 400. Minus, and let's see here. Actually, it's a plus, is it? Negative. Those 2's, I can cancel those out. And I can write that as x over square root 400 minus x squared. All right, let's do a couple of things. First of all, I don't like that complex fraction, so I'd like to multiply by 400 under the radical to clear that out of there. But since that 400 is under the square root, if I multiply the top by the square root of 400, or 20, it would be the same thing. So that would give me -400 over x times the square root of 400 minus x squared. Now looking at that, I almost have a common denominator in that second term. All I need is the x out here. So let's multiply this guy by x over x. Okay, so I now have x squared minus 400 over x times the square root of 400 minus x squared. We are so close to something really nice, I'm going to go ahead and multiply this top and bottom by the radical to clear the fraction. So I have on top x squared minus 400 times that radical, and on the bottom I would have x and then the square root times itself, 400 minus x squared. These are not quite the same, just the terms are reversed. So essentially, if I divide them, I'm going to get negative 1, right? If you want, you could think of factoring out a negative 1 from one of them before you cancel. So we end up with negative square root 400 minus x squared over x. Not too bad.